Hello everyone and welcome to this new video where we're going to explore sequence-to-sequence models. This is the architectures that justifies the existence of the LSTMs or long short-term memories. It is the technology behind massive breakthroughs in machine translation, like in Google Translate. With this model, they were able to replace thousands of lines of rule-based code with just a single model trained on data. So by the end of this session, you'll be able to understand the theory of how we map one sequence to another using the Encoder-Decoder framework. By the way, I'm using a presentation automatically generated by Notebook LM. I have a video on how to do that, and I've used this paper by Google and some insights from 2 YouTube videos published by StatQuest and Weights and Biases, both YouTube channels. Okay, so standard deep neural networks typically require inputs and outputs to have known fixed dimensions. For example, in image classification, the input is always a fixed grid of pixels. But human communication is not fixed. Sentences have random lengths. To make matters more difficult, the input does not match the output. So we need a domain-independent method that makes minimal assumptions about the sequence structures. So LSTM or RNN. Let's look at an example that we're going to use for this presentation to better understand. We want to understand the English phrase hello world into the French bonjour le monde. Here's the core challenge. The input has 2 tokens, but the output has 3 tokens, bonjour le monde. We cannot simply map the first one to the first one because we have different structures and lengths, so this final word wouldn't have a matching one. We need a system that can digest the 2 input tokens and somehow understand that it needs to generate 3 output words to capture the same meaning. Here we're assuming that 1 token is 1 word. It's 1 word. In real life, that's not the case. 1 word can have 2 or more tokens depending on the length and the model used to create the tokens. But this is not in our scope. There are many other examples where this, because this framework is flexible, it can be used for arithmetics. Like, for example, if we have an input, what's 10 plus 12? If you ask, for example, ChatGPT, what's 10 plus 12? ChatGPT actually doesn't have an internal calculator or something to make this calculation, but it turns it into a string. And then the most probable output should be 22. So it would spit 22, not because it made a calculation, but because it is the next most probable token or word. It's also useful in conversations like we have an input, how are you, I'm fine, or like translate code from Python to C++. To solve the variable length problem, we'll use an encoder-decoder framework, as we said. We'll split the model into 2 parts. The encoder part that will read the input sequence 1 token at a time and compresses it into fixed dimensional vector representation. This one. And then the decoder takes this vector and extracts the output sequence. We typically use the long short-term memories, as we said, for both parts, this one and this one, because they are excellent at learning long-range temporal dependencies. In this example, we're going to use only one layer of LSTM at each step, but in real life, we can have more layers. So, for example, A would have this network, and then the output should go to another layer and then goes here, then go to the second layer. We can have even more layers, but this is a simple example. So let's trace our example. First, we need the word hello into the encoder LSTM. Note that we can't feed the raw texts. The first pass it through an embedding layer to convert the word into numbers. The LSTM processes hello and updates its internal hidden state and cell state. It now remembers the start of the sentence. Next, we're going to feed the word word. When we say unroll the LSTM, we mean we are using the exact same LSTM cell with the exact same weights and biases. We feed the embedding for word into the LSTM along with the hidden state from the previous step. Now the LSTM combines its memory of hello with the new information word. After processing the second word, the encoder is done. The final internal state, hidden state, are what we call the context vector. This one. This is a context vector. This is a crucial concept because this signal's fixed size vector must encode the entire meaning of hello world. It is the bottleneck of the system. We discard the individual outputs of the encoder. We only care about this final state. So we will only care about this. That would represent our phrase. Okay, now we're going to switch to the decoder. How does the decoder know what we said? We take that context vector that we generated and use it to initialize the hidden and cell state of the decoder, LSTM. Ideally, the decoder now starts its process or thinking process about the concept of hello world. Note that the decoder needs this token as a starting token to know that we're starting. So SOS stands for start of sentence. So always in the decoder, we're going to start with SOS and then start the process, and it ends. How does it know that this is the last token? It should spit out end of sentence. So we start by feeding it start of sentence token, and it will keep rolling or thinking until it spits out end of sentence. So the decoder, as you said, needs an input. Since it hasn't said anything, we feed it a special token called start of sentence. The decoder runs the math using the context vector and outputs a probability distribution over all the French words. In our example, the word with the highest probability is bonjour. This is where the magic happens. We take the predicted word and feed it into the decoder as the input for the next time stamp. So the decoder updates its internal states again and predicts the next likely word, which is le. This loop allows the model to generate a sequence of any length. and this is what we want. We repeat the process. Le generates mond, and so on and so on. Notice that we took 2 inputs, but the model generated 3 words plus the stop token. So we successfully handled the length mismatch. So how do we train this? Let's go back to previous slide. If the untrained model predicts the wrong word at step 1, so let's say it started with another French word that would not make sense in our case. Let's say it started with, I don't know, a random word. The rest of the sentence would not make sense, so it would make the training very slow. In that case, we will use a technique called teacher forcing. Here, let's say after the first token that we input, that is start of sentence, instead of bonjour, the output was banana. What we do is, even though it predicted banana, we manually feed it bonjour in the next LSTM cell. This is what we call teacher forcing. So it doesn't matter what the previous LSTM made as a prediction or an output. In all cases, we will input the correct one in the next LSTM, because we don't wait for the model to fail. During training, we ignore the model's prediction and feed the correct previous word into the next step. This helps the model learns the correct pattern much faster. Again, we call it teacher forcing because it simulates like a teacher in a class. For the inference strategies, we have 2 main strategies. There is greedy decoding, which pick the best word now at each step. So because bonjour had the highest probability, we would select it now and then go to the next one, also select the highest probability. There is also another method which is called the beam search. We will take this one, the first one with the highest probability, but we keep these other probabilities alive or in memory. Do the same for the next step. So pick the first one, but also keep the other 2. And then we calculate the probabilities of all of the sequence and get the highest probability, the phrase with the highest probability. There is an optimization technique, which is famous trick from the original paper. It's called reversing the source. So instead of hello world, we feed in word hello. Why do we do this? So instead of ABC, we put as an input CBA. Not instead, but it's an optimization. So in next steps. So why do we do this? This places the last word as the input immediately adjacent to the first word of the input. So hello world, and then here we're going to put word hello. This forces like the last word to be adjacent to the first one. Let's say we have a longer phrase like hello my word. It would force word my hello to be close together. This introduces short-term dependencies, making it easier for the long short-term memory to establish a connection between the input and output during back propagation. This theory is a very powerful technique, but it has a flaw. We are compressing the entire meaning of the sentence into a single fixed vector. So if the sentence is very long, the model tends to forget the beginning of the word. Here we used only 2 tokens, but in real life, like let's say we have a whole book, by the end of it, we would start forgetting the beginning of the book. So we have to check again and etc. So this is where attention is introduced. In future sessions, we will discuss the attention mechanism, which solves this problem by allowing the decoder to look back at specific parts of the encoder, removing this bottleneck. So in summary, we have input encoded, it would spits out the context vector and then passes through the decoder, and we will have the output. We have the teacher forcing technique that would always gives the correct next word in the LSTM cell to force the model to learn faster. We have beam search that combines the whole output and then gives us the one with the highest probability by remembering all the other alternatives, and this optimization technique that we put the reverse phrase as an input to force the model also to learn better. So that's all for this video. Thank you for watching.